Computational problem number 3. I'm glad I'm getting to this because I know you guys were really anxious about these poor birds. So, this is what we have. An industrial-sized glass bulb has broken, leaving a long length of nichrome wire still connected to the circuit, but now just stretched along the ground. Nichrome has a resistivity of 1.1 times 10 to the minus 6 ohm meters, and the wire has a radius of 0.6 millimeters. The wire carries a current of 5 amperes. A sparrow lands on the ground with its legs touching the wire 2 centimeters from each other. A sparrow hawk follows and lands on the same wire. We actually had a sparrow hawk land in the little atrium outside our offices a little while ago. No one knew what it was, but I passed the picture around to someone who was an ornithologist and said, "Oh, that's a sparrow hawk." Actually, it might have been a goshawk now that I think about it. I don't know what the difference is. I'm not an ornithologist. Okay. With its feet touching the wire 4 centimeters apart from each other. Assume the total resistance of each bird is 2 ohms, and the bird will keel over if it gets a current of greater than 75 milliamps. What happens to the birds? And I do say be careful with your units on this one. Okay, so this is what we have, and the real question is, well, the same question as everything, right? It's like this question, you know how to answer this question. You know how to answer this question because I'm asking it to you, and I wouldn't ask you something you didn't know how to answer. Okay, so what we end up having is something that's just like this. We have a wire, it has some resistance, and we have a connection here and a connection here that happen to be the bird's legs, and we have some resistance here. So I'm going to label this RW for our wire and RB for our bird. And then what do we know? We know we have some current coming in here. So there's 2 ways to do this. I'm going to try to do them very quickly. The first way is the way that I intended it for it to be done, and the way that however, it's an approximate method. Okay, so first way that I would do it is just this. We have some I coming in here. We have a resistance here. Therefore, what do we have? We have IRW. This is, I'll call this IT for I total. The total current, so the voltage drop from here to here, before the bird lands on this, the voltage difference from here to here is just ITRW. That's it. Okay? And this would be delta V. Then my plan would be, gosh darn, I forgot to give you guys the strategic outlines right at the beginning. Oh well, we can talk about that in class. The plan here would be to look at this delta V, to look at this RB and say, all right, we know Ohm's law, V equals IR, I equals V over R. So therefore, this delta V over RB, and then all we need to do is compare this to our threshold current and say, is this higher or lower than the threshold current, to determine whether the bird is alive or not. Okay, so that's the strategy. So what do we need to know in order to get this RW? Well, we know resistivity is 1.1 times 10 to the minus 6 ohm meters. Yep, it is ohm meters. And we know that the radius is 0.6 millimeters, which is 6 times 10 to the minus 4 meters. And we know that the resistance is equal to rho L over A. I'm actually going to change this into resistance per unit length because it's going to make our life a little easier. So I'm just going to take this L and divide it over here. You don't have to do that. I'm just doing it for my own purposes because I set this problem up so that we have 1.1 times 10 to the minus 6 ohm meters, and that we end up, when you do this pi r squared for this, A equals pi r squared, when you do that, it ends up being 1.1 times 10 to the minus 6 meters. So what does that mean? We have 1 ohm per meter is our resistance per unit length. Okay, so now this makes it really easy to look at our 2 birds. So now these are the equations we have. We have the volt delta V is I T R over L, which we have just calculated over here, times the L bird, LB, which is the length of the distance between the two birds' legs. So this is now ITRW. This is the resistance of the wire. RB we are given, right? So we know that this is a delta V right here. So we know V over RB. We know this equals our I bird. So let's go ahead and do this for the sparrow. So we'll call this L sub S. Well, as a matter of fact, I won't even worry about it. I'll call it I sub S for I sparrow. And we know that the I total, I believe, was 5 amps. Yes. So we have 5 times 1 ohm per meter times 0.02 meters over 2 ohms is what we end up having. And we can kind of play around with some various things to make our lives a little bit easier, and we end up seeing that this is 0.05 amps or 50 milliamps. Our sparrow, this is for our sparrow, and we know our sparrow is going to be able to flit away at the end of the day. So now let's do this exact same thing. Yeah, I'm just going to do this. We're going to do this exact same thing. Oops, I didn't even need to erase that. For now, our sparrow, what's the only thing that changes for the sparrow hawk? I'm sorry, this is SH now, the sparrow hawk. The only thing that changes is the distance between the legs. Distance between the legs is now 0.04 meters. So we have 2, this turns into a 2, and so you will note this is now 0.1 amps or 100 milliamps. Our threshold was 75, so our sparrow hawk is going to keel over. Okay, I told you I would give you the exact solution. This is an approximate solution, and you will see that the exact solution is not that much different. So the exact solution, and if you had done this, you would also get full credit for this also, of course. As a matter of fact, maybe you'd even get bonus points because I know Sharon always wants bonus points. Okay, where are we? Oh, this is where we are. We're in the same picture we had before. We have the R of the wire. We have the R of the bird. We have the R of the bird. And we have a current that's coming in. But now this time, let's use our knowledge of electric potential, Kirchhoff's loop rule, whatever you want to call it. What we know is the voltage drop between here and here are equal, whether it goes through here or through here. So we have an IB, a bird current, and we have an IW, a wire current. Sorry, that's not supposed to, this is supposed to be a separate thing. IW, which is the wire current, and we know that IB, RB, the voltage drop here, has to equal IW, RW, which is the voltage drop here, right? And this is just, once again, this is just conservation of energy. So you will remember we've had many discussions about that. All right, and what else do we know about this? Well, we know that the I total is equal to IB plus IW. And so we're just going to do some very simple algebra. And let's see, what do I want? I want IW in terms of IB. Yeah. So IW is equal to IT minus IB. Doesn't get much simpler than that for algebra. I'm just going to substitute that into here. So we now have equals IT minus IB, B times RW. And let's do a little bit more algebra. ITRW minus IBRW equals IBRB. And once again, just super simple. So we have IB times RB plus RW equals ITRW, which is IB equals ITRW over RB plus RW. Okay, so just reminding ourselves what all these things are. This is the bird current. This is the total current. This is the resistance of the wire. This is the resistance of the bird. And this is the resistance of the wire. So now it's just a matter of putting these numbers in. We already have calculated all these numbers, so it becomes super easy. So now we have our sparrow current is just going to be this RW. Remember, it was 1 ohm per meter, so that's 0.02 meters, so it's 0.02 ohms. So we have 5 amps times 0.02. Whoa, Nelly. Sorry. Okay. So the IT times RW for the sparrow. Plus RB is the 2 ohms for each of them. So this is 2.02. So what do we have? This is 0.1 over 2.02. Well, what did we estimate it was before? We thought this was about 50. We thought it was exactly 50 milliamps. In this particular case, it ends up being something like, I don't know, 49.8 milliamps, something like that. So you can see it's changed a little, but you also see why the approximation is just fine. Okay, now, and you do the same thing. The only difference, remember, is that this 0.02 turns into a 0.04. And so what you have is 5 times 0.04 over 2.04. And this is roughly, well, not roughly, it is 0.2 over 2.04, which ends up being something like 0.984 or something like that. So instead of being, oh, I'm sorry, it is 0.0. I made a mistake there. 0.0984. So 98.4 or something really close to that milliamps instead of 100. One way or another, this sparrowhawk is not in good shape. Okay. Okay, so now we know the answer. All right, that was computational problem 3.